let's continue. Okay, let me open the table of content first. Okay. Okay, we are still in chapter 20, patching smaller tables, and still on homework simulation. Let me open that. This one. Okay, homework simulation. Let's read the readme case. Okay, and then which one? Small table. Okay, the readme here. Okay, this fun little homework test. Oh, wait a minute. Okay, the chat disconnected. Alright. Okay. This fun little homework test, if you understand. This fun little homework test, if you understand how a multi-level page table works. And yes, there is some debate over the use of the term fun in the previous sentence. The program is called Paging Multi-Level Translate.py. Some basic assumption. Okay, the page size is unrealistically small, 32 bytes. Okay, the virtual address space for the process in question. Assume there is only one. Okay, it's 1024 bits or 32 kilobyte. Okay, guess you are wondering. I think it is. Wait. Maybe something like this. Right. So it is a 10-bit. What is it called? Oh, no. 1024. Okay. 1024. Alright, so maybe something like this. This is the address space, right? Let's check the exponent of that, I guess. 15, okay. So maybe it is the 15-bit address space. And we have 1024 bits in this address space. I guess something like this, right? So the 15-bit address space divided by 32 byte, which is the page size. So we have 1024 bits in this 15-bit address space, with one page is the size of 32 byte, something like that. Okay. Physical memory consists of 128 bits. Oh, okay. So the virtual address space have more bits than the physical memory. Is that it? I think there's not much option, I guess. Number of virtual page allocated, number of virtual address to generate. Okay, so yeah, we cannot control this one, cannot change this one. All right, at least from the option here, we might be able to change that in the source code itself. But for this simulation, this is the assumption. Okay, those a virtual address need 15-bit, right? 5 for the offset, something like this, because this is the bit size, right? 5-bit offset, and then 10-bit for the virtual page number. A physical address requires 12-bit, right? Because this one. Okay, the page size here is also, what is it called? Is also affecting the physical memory page, I guess. Something like this, right? So it is the 12-bit physical address space with 5 offset and 7 page frame number. Okay. Yeah, this is interesting. And if I remember correctly, previously we assumed that the virtual address space is less than the physical address space. Now the assumption is the opposite. The virtual address space is bigger than the physical address space. Okay. The system assumes a multi-level page table. Thus the upper 5 bits of a virtual address. The system assumes a multi-level page table. Thus the upper 5 bits of a virtual address are used to index into a page directory. Thus the upper 5 bits of a virtual address are used to index into a page directory. Okay, the system assumes a multi-level page table. Thus the upper 5 bits of a virtual address are used to index into a page directory. The page directory entry, or PDA, if valid, points to a page of the page table, right? This is the page from the linear page table. You can think of it like that. Or maybe the page of the address space, maybe. Okay, it's page table page. Page table page. Okay. It's page table page hold 32 page table entries, or PTA. Here, it's page table entry invalid. Again, invalid. Hold the desired translation. physical frame number or PFN of the virtual page in question. Okay. Yeah. Why didn't write this as page of the page table? Yeah, but that's nitpick, I guess. But changing the term might confuse someone, you could say. Okay, hold 32 page table entry, right? So it's page from, let's say, from this page 1024 page, hold 32 page table entries. If you are in chapter 20, I feel like the figure 20.3 make it easier to understand what it means. Yeah, this one. This is the page of page table from this one, right? This is the linear page table, right? And then from this linear page table, we divide the page entry into what is it called? Into the page according to the page size. So from this linear page table, we kind of chopping up this this page entry into multiple pages. In this case, we are chopping up into, what is it called? Into 4 page table entry. So one page here have 4 page table entry. Something like that. Okay. And then this is the page table entry for this page 201. And then the page 1 here. Okay, assuming we are starting from 0 here. This is page 0, this is page 1, this is page 2, and this is page 3. The page 1 here is not allocated, and then the page 2 also not allocated, but the page 3 is allocated. Right, okay. You can take a look at the figure 20.3 to understand this more. Okay, or helping you to understand the concept easier, something like that. Okay. The format of a page table entry is thus valid. Oh, page frame numbers 6 until page frame number 0, I guess. Wait, we have 5 offset, right? I wonder why this is page frame number 6. Oh, okay, right, this is 7 page frame number. Alright. Okay, 0 until 6. Okay. is basically, let me open this here, valid bits, and then page frame number 0 until page frame number 6. No, 0 until 6, right? So there is that. And is those 8 bits or 1 byte? Well, this, I guess this depends on the system, because some people say that on some system 1 byte might not be 8 bits, especially in those embedded system. But yeah, I haven't seen that, so I'm not sure yet. But that is something to keep in mind. The format of a PDA, or the page directory entry, is essentially identical, right? Okay. Page table 6 until page table 0. You are given 2 pieces of information to begin with. First, you are given the value of the page directory base register, which tell you which page of the page directory is located upon. Second, you are given a complete dump of each page of memory. A page dump looks like this. Okay, first we are given the page directory base register, which tell us which page the page directory is located. Okay, the base register, or maybe the base address, something like that. Which page of the base directory is located. Okay, and then dump of each page of memory. Okay, this is the page dump. I am not sure. Is this the hex number? Maybe. It shows the 32 byte found on page 0, 1, 2, and so forth. Oh, 32. Wait. This really 32? Yeah, I want to check. Oh. Maybe. Okay. 32 bytes. So this one is 1 byte. Is that it? The representation of 1 byte. And there are 32 of these. Okay, maybe the first byte, 0 byte on page 0 has the value. Oh, okay. 0x 08. The second is 00. Okay. The third is 01 and so forth. Alright. given a list of virtual address to translate. Okay, let me take note of that. First thing first, get base directory, base register, right? And then get page dump 32 bytes in a page, I guess. A list of virtual address to translate. List virtual address to translate. Okay. Use the PTBR or the base directory base register to find the relevant page table entries for this virtual page. Then find if it is valid. If so, use the translation to form a final physical address. Using this address, you can find the value that the memory reference is looking for. Use the translation to form the final physical address. Using this address, you can find the value that the memory reference is looking for. Oh, interesting. I mean, so far, if I remember correctly, we are only translating from the virtual address to physical address. And are we gonna get the value too? I mean, from those physical address. Okay, well, let's see how it goes, I guess. Of course, the virtual address may not be valid and thus generate a fault, like this one. Some useful option. Okay. Oh, looks like this one is not in the README yet. Okay. Change the sheet to get different problem as always. Change the number of virtual address to generate to the more transaction for a given memory term. Use the C or solve to show the solution. I thought C stand for compute. Wait a minute, let me check. Oh, not okay. Yeah. No, what is it called? Not double test like this. Is that always the case? No, I'm kind of curious. Oh, look, maybe this one also didn't have the double test equivalent like this. Okay, interesting. Yeah, I'm just curious. Good luck with this monstrosity. Okay. Looks like this is gonna be another challenge. Well, let's find out, I guess. I mean, the fact that the readme, unlike other readme, didn't give no, not that one, didn't give an example like this, right? Running the script without argument example and then giving this kind of explanation for the translation is something new, I guess. Right. Okay, let's find out. Okay, we already have cell bank here, and I assume it is already inexecutable. Right. It is executable, okay. Yeah, it has an executable permission, the X here. Just something to keep in mind. Yeah, running this without any argument. Oh. What? Yeah, I think this term is correct. This monstrosity. Okay, yeah, it's something. Let's put it that way. Oh my god, what is this? Is this 32? Let me check. Wait. Looks like this is 64 character instead of 32. Allocated 64. Huh. Should I change that? No, not. Wait. Oh, the default is 64. But the assumption is 32. Wait a minute. Right. The assumption is 32 byte. So why is the default 64? I'm confused. It's still 64 though. So maybe not that one. Maybe. Yeah, I'm not sure which 32. That we are talking about here. Okay. don't even know where to start. Okay, virtual address. Yeah, I need to learn how to read this hex number, I guess. At some point. I don't know when. You know what? Let's take an example. Okay, compute. Yeah, let's try analyze this. How do we do the translation? Hex to, I guess, decimal converter. Convert 24. Okay. And it seems like, at least from the solve here, OS translate. Oh, so we are using the Python library. Okay. Wait, or maybe let's take a look at this. Is there any? No. Okay. Oh, is this from? Wait a minute. Oh, okay. Yeah, it looks like. Okay, it is from this OS class, not from the OS. What is it called? Not from this operating system interface from Python. Okay, yeah. I guess so. So this is the translation. PID, okay. Get bits directory entry. Okay. Yeah, why we use this one? 80. Let me check. Oh, 128. So that is the max here. You know what? Let's check this out. And 0. Oh, what? Oh, wait a minute. Memory. Oh, this is the virtual address, and then the max here. What is this again? Oh, okay, this is the max. So we are removing the rest. Okay. Right. Okay, so maybe something like this. 2, 4, 5, 7. Okay. And then write save 10. Okay, the virtual page number. Okay, like this. 24. I kind of forgot. Maybe something like this. Okay. And then it becomes something like this. Maybe 16. 1, 2, 3, 4, 5, 6. Okay, and then 9, 12, 15, 19. Okay, something like that. Mm-hmm. 24. Okay, so this binary represent 24. Okay. Alright, this one. And then to get the address, I assume this is the base directory base register. It is 108. Maybe. And then left save by the page speed. The page speed is 5, right? To get the base address, thing like this, and then adding that to the page speed 24. Maybe. Okay, and then we got the base directory address, right? Get that in the memory. Yeah, I'm of curious. What is inside this memory? Physical memory. Okay. Or is this 0? Maybe inside the memory is 0. But when we initialize the page, the memory become inside the memory become this 1, which is 127. Is that what it is? Oh, but the value is different. Okay, so for now, let's assume that this is 127, I guess. Okay, 27 max by, or maybe let's use the hex representation. Okay, right. Max by this one. Oh, interesting. Okay. You know what? I'm kind of curious again. Okay, 1, 2, 3, 4, 5, 6, 7. Alright. What about this one? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Interesting. And now we're masking that. Isn't this gonna become 0, right? Is this right? I wonder if this is correct. You know what? Let's try printing that. Maybe something like this. How? Like how this is different. nice thing. Okay. Let me try understanding this. Okay, translate, right? But before that, before translate, okay, process unlock and then memory dump. Maybe this one. Okay. Init page there. Okay. Okay, that bit. So there's allocated virtual page and then fill page. Oh, maybe this is the one. Fill page, right? Maybe. Okay. So this one, the 7F, this one is only when we initialize the page, right? After that, we fill the memory with random number. Maybe something like that. Okay. I mean, if I don't know the random number, how did I know the value? And fetch what value? Right? Itu we. Oh. Trumpets. Oh, is this the one? Is this the value? Is that it? Okay, let me try. Okay, ptx content 21 33. Let me try. We are in the page 33, right? physical trace this one. One 724. I'm still not sure how to translate this. Like, is there any hint about the value? Well, let's continue this on the next session, I guess. Yeah, for now I print out the base directory entry here. But I'm not sure. "24". So maybe it is but this is 0. Oh, what? 127. Interesting. Is this one? Let me check. 64. I'm not sure if that is correct or not. Okay. What fetching? Oh, yeah, previously I add this. What is it called? I add new flag to make translating easier on the linear page table simulation, and I might do the same for this, but let's see if there is some information in this one. Yeah, I'm kind of curious what should we do with this information. You know, like page 103 with this hex number or byte maybe. Okay, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.